In the summer of 1942, I received a memorandum that made me consider abandoning the entire project. Edward Teller had run preliminary calculations. His conclusion? Detonating an atomic bomb might ignite the atmosphere of Earth. All of it. A self-sustaining nuclear reaction spreading across the planet. Every nitrogen atom fusing with every other nitrogen atom until nothing remained but ash and radiation. I read his numbers. I could not immediately find the error. For several weeks, I worked through the physics myself. If Teller was right, we were not building a weapon. We were building a device that could sterilize the planet. One test, and humanity ends. This was not a small probability concern. Teller's initial calculations suggested the reaction might actually propagate. I had to decide. Do we continue? Or do we stop everything until we know for certain? Let me explain what Teller found, why it terrified us, and how we eventually proved it wrong. This calculation, performed in secret, never published during the war, may be the most consequential physics problem ever solved. The physics of atmospheric ignition. The concern was straightforward. Our bomb would create temperatures exceeding 50 million degrees Kelvin at the moment of maximum compression. The surface of the sun is approximately 5,800 Kelvin. The core of the sun is approximately 15 million Kelvin. We were creating conditions hotter than the center of a star. At such temperatures, atomic nuclei move with enormous kinetic energy. They collide violently. If two nuclei collide with sufficient energy, they can overcome the electrostatic repulsion between their positive charges and fuse together. This is nuclear fusion, the same process that powers the sun. Earth's atmosphere is 78% nitrogen, 21% oxygen, and roughly 1% argon and other gases. Nitrogen nuclei contain 7 protons each. When 2 nitrogen nuclei fuse, they could theoretically produce silicon-28 or various other products depending on the reaction pathway. The question was, if we created a region of 50 million degrees, would nitrogen-nitrogen fusion release enough energy to heat the surrounding nitrogen to fusion temperature? If yes, the reaction would propagate outward. The atmosphere would burn. Teller's preliminary calculations suggested this might happen. Why nitrogen fusion is different from hydrogen fusion. The sun fuses hydrogen, not nitrogen. This distinction is critical. Hydrogen nuclei, single protons, have charge +1. When 2 protons approach each other, they must overcome electrostatic repulsion. This repulsion is described by Coulomb's law. The force is proportional to the product of the charges divided by the square of the distance. For 2 protons, force proportional to 1 times 1 equals 1 in appropriate units. For 2 nitrogen nuclei, each with charge +7, force proportional to 7 times 7 equals 49. The repulsive barrier for nitrogen-nitrogen fusion is 49 times stronger than for hydrogen-hydrogen fusion. This is called the Coulomb barrier. To overcome it, nuclei must approach within approximately 1 femtometer, 10 to the -15 meters, where the strong nuclear force takes over and binds them together. The energy required to reach this distance scales with the square of the charges. Nitrogen requires vastly more energy than hydrogen. At 15 million Kelvin, the sun's core temperature, hydrogen fuses readily. Nitrogen does not. The sun does fuse some nitrogen through the CNO cycle, but this requires nitrogen to capture protons, not to fuse with other nitrogen nuclei directly. Direct nitrogen-nitrogen fusion requires temperatures above 100 million Kelvin under most conditions. The cross-section problem. Temperature alone does not determine whether fusion occurs. You must also consider the reaction cross-section. Cross-section is a measure of probability. It describes how likely two particles are to react when they collide. The unit is area, typically measured in barns, where 1 barn equals 10 to the minus 24 square centimeters. Cross-section depends on energy. At low energies, cross-section is essentially zero. The Coulomb barrier prevents any reaction. As energy increases, cross-section rises. But even at high energies, cross-section has a maximum value determined by quantum mechanics. For nitrogen-nitrogen fusion, the cross-section at relevant energies is extremely small. Even when nuclei have enough energy to overcome the Coulomb barrier, most collisions do not result in fusion. The nuclei scatter elastically. They bounce off each other without reacting. Teller's initial concern was based on extrapolating cross-section data from lower energy experiments. The extrapolation suggested higher cross-sections than actually exist. Hans Bethe's calculation. Hans Bethe was the world's leading expert on nuclear reactions in stars. He had won the Nobel Prize for explaining how the sun produces energy. If anyone could calculate whether atmospheric ignition was possible, it was Bethe. I asked him to lead a team to resolve the question definitively. Bethe's approach was systematic. He considered 3 questions. First, what is the actual cross-section for nitrogen-nitrogen fusion at temperatures achievable in an atomic bomb? Second, if fusion occurs, how much energy is released per reaction? Third, how does this energy compare to the energy lost through other mechanisms? Energy production versus energy loss. This is the critical comparison. For a reaction to be self-sustaining, energy production must exceed energy loss. In the center of an atomic bomb fireball, energy is lost through several mechanisms. Radiation losses. Hot plasma emits electromagnetic radiation. At 50 million Kelvin, this radiation is primarily X-rays. The power radiated scales as the 4th power of temperature. Double the temperature, and radiation increases 16-fold. Expansion losses. The fireball expands rapidly. As it expands, it does work against the surrounding atmosphere. This work converts thermal energy into kinetic energy of expansion. The temperature drops. Conduction losses. Heat flows from hot regions to cold regions. The boundary of the fireball conducts energy outward into the cooler surrounding air. For atmospheric ignition to occur, nitrogen fusion must produce energy faster than all these loss mechanisms combined. The calculation. Bethe calculated the nitrogen-nitrogen fusion rate at 50 million Kelvin. The fusion rate depends on 3 factors: the density of nitrogen nuclei, the cross-section of the relevant energy, and the velocity distribution of the nuclei. which depends on temperature. At atmospheric density, approximately 2.5 times 10 to the 19 molecules per cubic centimeter, and 50 million Kelvin, the fusion rate was extraordinarily low. Why? Because even at 50 million Kelvin, the average nitrogen nucleus does not have enough energy to overcome the Coulomb barrier. Only the extreme tail of the Maxwell-Boltzmann distribution, a tiny fraction of nuclei with far above average energy, can potentially fuse. This fraction is exponentially small. The Gamow factor describes this suppression, xp minus pp, where eta is equals z1 z2 e squared over NV, with z1 and z2 being the nuclear charges, e the electron charge, and Planck's constant divided by 2 pi, and v the relative velocity. For nitrogen-nitrogen, z1 equals z2 equals 7, the Gamow factor at 50 million Kelvin is approximately 10 to the minus 12. Only about 1 in a trillion collisions involves nuclei with sufficient energy to overcome the Coulomb barrier. Even among those collisions, the cross-section is small. Perhaps 1 in 1,000 of barrier-penetrating collisions actually results in fusion. Combined probability, approximately 10 to the minus 15, 1 in a quadrillion. Energy balance. Now compare energy production to energy loss. Nitrogen-nitrogen fusion releases approximately 10 MeV per reaction, 1.6 times 10 to the minus 12 joules. At the calculated fusion rate, energy production in 1 cubic centimeter of air at 50 million Kelvin is approximately 10 to the 8th joules per second. Radiation loss from the same cubic centimeter, calculated from the Stefan-Boltzmann law applied to the plasma, is approximately 10 to the 16th joules per second. Energy loss exceeds energy production by a factor of 100 million. The reaction cannot sustain itself. The fireball will cool by radiation far faster than fusion can heat it. Why the fireball cools so quickly? Consider the time scales. The fusion time scale, how long it would take for fusion to significantly heat the plasma, is approximately 10 to the 8th seconds at these conditions, millions of years. The radiation time scale, how long it takes for the plasma to radiate away its energy, is approximately 10 to the minus 6 seconds, microseconds. The expansion time scale, how long it takes for the fireball to expand and cool, is approximately 10 to the minus 3 seconds, milliseconds. The fireball dissipates in milliseconds. Fusion would require millions of years to add significant energy. The disparity is not close. It is a factor of 10 to the 14, 100 trillion. What about hydrogen in the ocean? Teller raised a secondary concern. The oceans contain enormous quantities of hydrogen in water molecules. Hydrogen fuses much more easily than nitrogen. If the bomb would detonate it over water, could it ignite the ocean? Bethe analyzed this scenario as well. Water must first be dissociated into hydrogen and oxygen. This requires energy. The hydrogen must then be heated to fusion temperature, approximately 100 million Kelvin for deuterium-deuterium fusion. But ordinary hydrogen, protium, requires even higher temperatures because the reaction proceeds through the weak force. The energy required to heat ocean water to fusion temperatures vastly exceeds the energy an atomic bomb produces. The bomb would vaporize water in its immediate vicinity, but the temperature would drop far below fusion threshold within meters of the detonation point. This scenario was also impossible. The 3 in 1 million after Bethe's analysis, we concluded that atmospheric ignition was impossible. Not improbable, impossible. The energy balance made it categorically excluded. But the report included a caveat. The calculations depended on measured and theoretical cross-sections. If those cross-sections were wrong by orders of magnitude, if our understanding of nuclear physics was fundamentally flawed, the conclusion might change. Bethe estimated the probability that the cross-section measurements were wrong by enough to change the conclusion at approximately 3 in 1 million. This was not the probability of atmospheric ignition. This was the probability that our basic nuclear physics was wrong in ways that would make the calculation unreliable. We accepted this uncertainty because we had no reason to doubt the fundamental physics. Cross-section measurements from multiple laboratories agreed. The theoretical framework, quantum mechanics and electrodynamics, had been validated across many experiments. The 3 in 1 million was an estimate of unknown unknowns. The possibility that something we could not imagine was wrong with our physics. Why we proceeded. Some have asked, how could you proceed with any non-zero probability of destroying the world? Here is my answer. The 3 in 1 million was not a probability of catastrophe. It was a probability that our physics was wrong in an unspecified way. If our physics was wrong enough to make atmospheric ignition possible, then our entire understanding of nuclear reactions was wrong, including our understanding of how the bomb itself would work. In other words, if the physics permitted atmospheric ignition, the bomb probably would not function as designed anyway. The same cross-sections that made ignition impossible also made the bomb possible. We were not gambling on a 3 in 1 million chance. We were accepting a 3 in 1 million chance that our fundamental understanding was wrong, in which case all predictions, including this one, would be unreliable. Additionally, the alternative, allowing Nazi Germany to develop atomic weapons first, carried probability of catastrophe that we estimated as much higher than 3 in 1 million. The deuterium side calculation. There was one more concern that received less attention publicly. Deuterium, heavy hydrogen, is present in all natural water at approximately 0.015%. Unlike ordinary hydrogen, deuterium fuses through the strong force, not the weak force. Its fusion cross-section is much larger. Could the bomb ignite a deuterium fusion reaction in the water vapor present in air? Water vapor in air is typically 1 to 4% by volume. Of that water, 0.015% is heavy water containing deuterium. The total deuterium concentration in air is approximately 1 part per million. At this concentration, deuterium fusion, even at temperatures where it would occur readily, cannot sustain a chain reaction. The mean free path for a deuterium nucleus to encounter another deuterium nucleus is too long. The reaction cannot propagate. This was verified separately. After Trinity. On July 16, 1945, we detonated the device. The atmosphere did not ignite. This was not surprising. We had high confidence in the calculation, but there is a difference between mathematical confidence and watching the actual test. In the moments after detonation, I watched the fireball rise. It expanded exactly as predicted. It cooled exactly as predicted. The reaction did not propagate. The physics worked both ways. The same principles that allowed us to build the bomb also guaranteed that it could not destroy the atmosphere. What the calculation revealed. This episode reveals something important about existential risk assessment. We faced a scenario where preliminary calculations suggested catastrophic possibility. We did not dismiss the concern. We did not proceed on hope. We assigned our best physicists to the problem and demanded rigorous analysis. The analysis showed the concern was baseless, not because we got lucky, but because the underlying physics made it impossible. This is the correct response to existential risk claims. Not dismissal, not panic. Careful calculation. The modern relevance. Today, similar calculations are performed for other potential catastrophic technologies. Particle accelerators have been analyzed for the possibility of creating stable strangelets or microscopic black holes. In each case, the physics has been calculated and the risks have been shown to be zero or negligibly small. The approach is the same. Identify the concern, calculate the relevant physics. Compare energy production to energy dissipation. Determine whether a runaway process is thermodynamically possible. In every case examined so far, runaway processes have been excluded by basic physics, usually by enormous margins, similar to the factor of 10 to the 14th that excluded atmospheric ignition. What we learned. The atmospheric ignition calculation taught us something about the relationship between physics and consequences. Nuclear weapons are extraordinarily destructive, but they are destructive within physical limits. They cannot destroy the entire atmosphere because the energy balance makes it impossible. They cannot trigger runaway fusion because the conditions do not permit it. This does not make nuclear weapons safe. They remain the most destructive technology ever created. A full-scale nuclear war could kill billions and potentially collapse civilization. But the destruction has bounds. Physics sets those bounds. The same physics that makes nuclear weapons possible also limits what they can do. The document, the full calculation, was classified during the war. It was referenced in the Los Alamos technical history, compiled after the war. The detailed physics was published by Bethe and others in subsequent years, once the basic concepts were no longer classified. The document is known as LA 602, Ignition of the Atmosphere with Nuclear Bombs. It remains one of the most important risk assessments ever performed. 3 physicists, Bethe, Teller, and Emil Konopinski, contributed to various stages of the analysis. Konopinski performed early calculations showing that deuterium ignition of the ocean was impossible. Bethe performed the definitive calculation showing nitrogen ignition was impossible. Final reflection. In 1942, I received a memorandum suggesting we might accidentally destroy all life on Earth. For several weeks, I did not know whether this was possible. We solved the problem through calculation, through physics, through the same mathematical methods that allowed us to build the weapon in the first place. The atmosphere cannot burn because energy dissipates faster than fusion can produce it. This is not luck. This is thermodynamics. The second law guarantees that isolated hot regions cool. They do not spontaneously heat themselves further. We did not merely destroy the world through ignorance. We verified through rigorous physics that destruction of that specific type was impossible. This does not make what we built less terrible. Nuclear weapons can still destroy civilization. They simply cannot destroy the atmosphere itself. The distinction matters. It shows that physics constrains consequences, that careful calculation can bound risks, that not every catastrophic scenario is physically possible. We checked, we calculated, we verified, and then we built the bomb anyway, knowing it could not burn the sky, knowing it would burn cities instead. That choice, the choice to proceed with a weapon of mass destruction, once we knew it would not destroy everything, may be the more troubling one. We could have stopped. We did not. The atmosphere was safe. Hiroshima was not.